Thank you for having me today. Really nice. It's a different kind of meetup that I've been used to, but still, I am very glad to be here. Hopefully today I can talk a little bit about failure and designing for failure, how software developers try to think how to design a system that is ready to fail, right? So it's a different concept, and I hope you all enjoy. So who am I? My name is Italo Vietro. I am from Brazil. The name does not like much of Brazil, but my family comes from Italy. I live in Berlin for about 5 years. Before Lykon, today I work at Lykon as head of technology. Before Lykon, I worked at N26, and even before I worked at HelloFresh for quite a while. And now it's a different challenge. I'm basically doing a lot of site reliability engineering things, and it's probably the topic that I like the most. And today I'm going to share a few of the things that I've learned from a lot of different people, a lot of experienced people, how we can build this kind of, reliable systems. So how do we design systems for the unexpected? That's the whole topic that I would like to bring us today. For quite a while, especially in my experience, when developing a system, we put reliability topics to the side. We focus on product development, and sometimes, when it fails, and then we kind of fix it later. It's a different mentality, I think, but that's why I would like to bring this kind of standards today and try to make sure we can put these standards up to the front and have this conversation with product people and, quality people and software developers, designers even, so everybody gets included and understand why we should prioritize reliability instead of paying off later. So a plane. Think about an airplane, right? So if you think about an airplane, I like to put this metaphor with software because airplanes fail all the time. If you think about it, when you're flying, there's probably some time in your life when you were flying that airplanes failed and you didn't notice. You just landed correctly, safely, but it failed. And it's an interesting thing. In 2019, there were 39 million flights across the world. It's quite a lot of flights. Out of those flights, unfortunately, 23 deadly crashes happened. Probably some of you heard about the 737 MAX case that is happening in the US right now. Right. So that one is one of the topics that software was involved in the failure. Software and process, but let's put the process aside. Software was involved in the failure. And those 23 deadly crashes, they actually caused, unfortunately, 287 deaths, which is unfortunate. It seems like a low number for the 39 million, but if you think about it, 287 people multiplied by their families and their problems that they have been facing through. And one of these flights is the 737 case, was actually caused by a software failure. So if you think about this, airplanes, they exist for quite a long time. It's more than 100 years now, I think. And recently, in the 90s more or less, they started developing a system that is called ELMS. This system stands for Electrical Load System, Management System. And this was created for failure, basically. They designed the system in the airplanes to make sure you have failovers, to make sure when your electric system stops, you have a mechanical system that actually keeps the plane running. It's interesting concepts from the aerospace kind of area, and also naval industries that I'm going to bring today, basically, and how they reflect in software. The Elm system was created to make sure if an airplane fails, like a battery fails, or you have an electric problem in your airplane, it keeps the essential runnings. This is a super important topic when you speak about software. If you think about the systems that you work with, can they work only with their essentials if the dependencies start failing, like databases or external APIs, or even if you use Kafka, your event system is failing. Can they actually keep running? That's a question that we barely think about, right, when we're doing our software development. I like this quote quite a lot. Resilience is a requirement and not a feature, by Liang Wu. And this is what I was talking a little bit about before, that we should put resilience as a requirement and not as a feature, right? It's not something that you can do afterwards. You should put this before. But of course, this is a whole cultural change in our industry that needs happening, and we're not quite there yet, at least most of the companies. So today I want to talk about a few of the standards that I've been working with and shared a little bit of the experience. So we're going to talk about latency control, load shedding, isolation, self-healing, and traffic control. So different topics that we can implement in our software on a day-to-day basis and have a little bit of more reliable systems. So we start with latency control. So a lot of the code that I put here, I'm a Go developer, so a lot of the code's examples are going to be in Go just for commodity, but you can easily translate that to your own language. So we're going to talk about timeouts. That's the first, most low-level thing that you can actually implement in your softwares. So we have different kind of timeouts when think about your systems, your services. We have client timeouts and we have server timeouts. Does anybody know what a client timeout is? Any idea? You can speak. No. Cool. Let me try to explain this. So the client timeout, if you think about a software or a system that you have, a microservice, and you have an external API, right? So you're accessing Google or whatever. You are the client for that. So basically, you have to protect yourself in case Google is down. Doesn't happen that often, but in case it does, you have to protect yourself, right? So normally, when creating your HTTP clients, you can literally set a simple timeout. In Go, that's basically how we do it. In a very easy and simple way. And then you need to set a specific timeout. In case that API hangs or doesn't respond, what does your service actually do afterwards, right? So there are many other kinds of timeout that most of the languages they actually support. In Go, you can be very specific on which level you want to support the timeouts, like in the DNS level or the handshake level, the TLS. So there is a lot of layers that you can actually define your timeouts. And depends on your requirements, but you should normally set those up. I know in Java, if you use Spring Boot, normally it has these defaults already set. It's not the case in Go, so if you don't set it, it's basically keep hanging there. So the thread is locked and you're just there. So defining the client timeout is always an important step to make sure if the API does not respond, you do something afterwards. So this is going to throw an error, and then we can handle it. This is just a more complex way of setting the context in Go in a different thread, so it doesn't hang the main thread. And then we don't call threads in Go, we call Go routines, but it's a similar concept. And then we have the server timeouts, which is the opposite side, right? It's like Google side. So on the Google example, like on the Google side, they want to make sure that the client that is calling there, if the connection hangs, it actually kills the connection so you don't keep your thread pool. You can distribute your threads across the thread pool. And this is how you do it in Go. You just set the HTTP server. So when you're setting up your HTTP server, you define your read timeouts, your write timeouts, your idle timeouts, and so on and so forth for every single connection you have. So normally servers, they handle read and writes, right? When you do a post, that's a write operation, so you have to actually time out in case you have like a too big request, a request is too big, and you have to time out because you cannot process, or you want to kind of handle your capacity in the server. Cool. Circuit breakers. Everybody heard about circuit breakers at any point in time? Someone? Cool. This is good. So circuit breakers is interesting. It's a concept that comes again from electrical industry. In your houses, definitely there is a circuit breaker, I hope. So it happens like that. In the software industry is the same way, right? When we develop a system, there is a way for us to protect parts of the code in case it goes off by something. So normally when setting up a circuit breaker in your houses, if the circuit goes off, like there is something happening, a circuit actually breaks, the circuit opens, right? So you actually don't have the connection anymore, and there is no risk of fire. The same happens here. It's just not fire, but it's the same happens. So let's say in this example, we're calling an external API, and let's say this external API fails 3 times and the ratio is 0.6. So let's say that the failure happens 3 times on that API. That API returns a 500 3 times out of the 0.6 length of the ratio. So in case it fails 3 times, the circuit will open and all the requests will stop going to that API, so the API can recover slowly and we stop calling it. This is super useful because now you can actually recover, like the API can recover, but you have to add something here so the service can actually come back and start calling that API. It's not automatic. For that, normally you add a retry. And the retry, it retries automatically a few times to see if that API is actually there. In case it is, then cool, the circuit closes again, and then everything else starts flowing. There is normally a dashboard that you can see circuits happening. This is a Hystrix dashboard. Hystrix was created by Netflix in Java. It's a very good pattern, basically, that they use, where you can see the distributed circuits that you have in your software. Those big balls over there, they're like the amount of requests you're getting, basically. So the bigger the circle is, the bigger the requests. If the circuit is open or closed, you can see on the like this, green thing. And if the circuit opens, you're gonna know, or your monitoring system is gonna know. And based on that, you know exactly what to do. As a software developer, you know something is going wrong and you should look into it. But normally, if you add the retries, then you can actually be safe, because once the API is back, the retry will do something. But you don't want to keep retrying every time, probably. If you retry every time, you're going to be overloading the API on the other side, or maybe it's going to be down for a few days, so you actually don't want to do this. So normally the Hystrix API, like in Java, is probably better to see, but basically they have a retryer, and there's many ways you can retry the software. You can retry linearly, so you can do like every 2 seconds try again, or you can do exponentially. So you can say, try in 2 seconds. If it doesn't work, try in 4. If it doesn't work, try in like 8, and so on and so forth. So you double all the time. And if it doesn't work, even after the 8 seconds, if it doesn't work for 4 times, for instance, stop. Stop trying, alert, and then call the on-call engineer, basically. So you can do something like that. This is super cool because then you can identify the issues before it actually affects your customers. So it's a super proactive mechanism. Cool. So load shedding is probably the most basic level of resilience. Normally happens when we are in the infrastructure level. Not even the developers, like the software developers, are going to touch much in this, but it's good to know that it exists. So especially when testing your APIs, you probably, you probably know the concept of load balancing, where you have a request, you have multiple servers, and it balances across those services depending on the algorithm you choose, right? It can be round robin, which is like randomly going afterwards, could be based on the load shed of the server. And basically load balancing algorithms are simple. You just load balance across different instances of the same server. There are many types of load balancing, which is basically based on the algorithm you choose, like round robin. There is another concept, which is the outlier host detection. So imagine that you have service B over there, have service A that calls service B, right? What do you do as a load balancer if one of those services are down, like that? So let's say it's down. Someone has to take it off the algorithm, so we make sure it doesn't balance there, so you don't actually cause errors to the customers. So that normally happens by this outlier host detection algorithm. This is normally implemented by Nginx. You guys know Nginx? Cool. So it's normally implemented by Nginx or HA proxy, which are technologies that do kind of the reverse proxy and load balancing. And that basically happens behind the scenes, so you don't even know it happens, which is cool. And then you keep these 2 services kind of balancing here and there. Once it's back up, then the algorithm takes back. So we jump into isolation. Bulkheads. Anybody knows Titanic? Yeah. Cool. All right, Titanic. Cool, so the Titanic, I think it set sail somewhere in 1912 or something. And unfortunately sank in the same trouble. There was a design failure there. And the design failure, well, this was supposed to be better resolution, but you can probably get the idea. It's a GIF. So you see the yellow lines, right? Those yellow lines are bulkheads, essentially. It was designed to contain the water in the ship. Fortunately, it didn't really work out. They had a design failure in the upper level of the bulkhead because they need to pass the air through the bulkhead because there were workers actually working there. If you watch the movie, remember the doors closing and the workers going underneath it? That was supposed to contain the water. Didn't really work because the water went up and then to the next bulkhead and then to the next. Unfortunately, it could only contain 5 bulkheads until it broke in the middle and then sank. So there was a design failure on the top where the water went through the vents and then to the next bulkhead and next bulkhead and next bulkhead. So what was the idea of the bulkhead? It's contingents, right? It needs to make sure whatever happens in there stays in there. So in software, whoops, that was too much. In software, it works in the same way. Basically, so the bulkheads, if you think about Java or Go, when you're calling an external API, you normally have a single thread that is doing that call, right? That single thread does that call. If that call freezes or hangs and you're not using a timeout or anything like that, your whole program is actually stopped by definition because the thread is working. But if you use a bulkhead, normally comes from the Hystrix example that I mentioned before on that dashboard. That pattern also covers this, which is saying, okay, you shouldn't have one thread actually doing the call. Try to distribute in multiple threads and make sure you balance the requests on those threads. So if the request actually hangs, one thread will be stopped, the others will work, and the main thread is still okay. It's still working, your application is still responding, everything will work as it's supposed to be. So that's the idea of bulkheads. Basically contain the problem in a single isolated area. If it fails, let it fail, handle afterwards. That's basically the idea of a bulkhead. Cool. Self-healing. So most of the applications that we deal with, especially when we're dealing in a microservice world, kind of, you want to have a health check. It's super useful also when you don't know what's happening. So when I'm on call, one of the first things I do is like, okay, something is failing. Let me look at the health check just to see what's happening on that server, if it's responding, if it's down, or if it's a dependency that is actually out. So we normally try to make sure these health checks are standardized. So I don't know, when you're designing your systems, one of the questions that I think it's super important to ask is like, what are my external dependencies? What are my dependencies at all? Like even not external, but inside. Do I depend on file system? Do I depend on a database? Do I depend on event broker like Kafka, like RabbitMQ? Or do I depend on Google? Something like that. So in this library, and there are many libraries, you can choose, let's say, here we have Google, and here we have a DB. So normally a DB is like something that your app needs to run, right? Like it needs to have that to run. But Google, well, maybe not. Maybe it's not critical for your business. So you can set it as false, and then you can have a standard reply. If everything is okay, you're going to get a 200 on the API level, and everything will be, well, working well. But if things are not really working so well, but your app still can respond to requests, then you're going to get still a 200, and the 200 here is very important, because this is used by load balancer normally to kick out of the algorithm your app. So if it's not 200, normally they kick you out and try to bring back up something a little bit healthier. But it says here the reason, like why is it failing and what is failing, so you can actually start investigating. But if everything is actually broken, then it's going to return a 500, and it will say, well, both of these things are actually failing, so you probably should look at it. The 500, again, super important. Load balancer, we use it to kick you off. So that's the main idea of a self-healing application. It knows what is going on. Now we need to self-heal. And to self-heal, one of the patterns is the outbox pattern. So does anybody here worked in a system where you have events going on, like Kafka or RabbitMQ or something like that happening in the backend? Okay, a few people. Cool. Normally, this is a super complex system to debug or to test or even to do anything, basically, because it's an event-driven system. When you're playing with an event-driven system, it can be very, very good for architecture because it's decoupled. So you don't have the, you're not calling directly an API. But your system is now more complex because you have events going on. And it's harder to test and it's harder to debug. Also, what happens is if your main broker, like Kafka in this example, is out. So you cannot produce messages anymore. So your consumers don't know what's going on. And let's say that this happens when a customer is doing a checkout. The checkout never happens at that time. The payment never happens at that time. Normally, there's an event that happens at some point that will go to a payment system that will then trigger the payment. But if you don't have Kafka there, how the payment system will know what order actually came in? To avoid that, normally we use the outbox pattern, which is, okay, we're going to put the messages in a database by itself. We're going to make sure it runs here. And then we're going to do, well, every time you have a message coming in, the sender will try to talk to Kafka. If Kafka is there, good, I'm going to send the messages. If not, I will hold on until it's back up. And then once it's back, the consumers get the messages and things just flow normally. So it's a good pattern that can be used not only for Kafka. Kafka was the example, but there are also external APIs or things like that. And this is basically how you do it in a simple way in Go. This pattern comes normally from C#. If there is anybody from the C# world, comes from there, and Microsoft. And this is the library that I wrote in Go, just in case. Cool. And then we have traffic controls. Rate limiters are probably the ones that are easy to catch. If you ever tested an API where if you do too many requests, you get a block, that's a rate limit, basically. And the way you implement it is super easy. Like normally you have in-memory storage, and you can say, well, in this API, I will have only 1,000 requests allowed per hour or per minute or per second. And then here you can stress test really. Like you can see how your server actually handles a lot of requests or not, and what kind of requests level you want to actually have or serve. Cool. So we've been through latency control, load chatting, isolation, self-healing, and traffic control, which is a lot. As a developer, imagine you having to implement all of that plus product development. We didn't even go to product development yet. So that's why normally resilience is neglected. Like a lot of people don't even try to implement all of that because it's a lot of things. When you have one service, that's all good. When you have 10 services, you still can manage. When you have 100 or 1,000, like Spotify, for instance, well, you cannot handle failure as you would in a single service anymore. You need help. You need someone else to do that for you. And that's a service mesh, normally. That's a service mesh that will do it. How are we on time? Sorry. We're good. Cool. So a service mesh is basically a concept that was brought to the development world, saying that, okay, all of this complexity will be abstract from the development world, and we're going to handle it for you while you do what you have to do for your business to keep running. So it's a pretty simple concept, but it's super hard to implement in reality. So anybody works with Kubernetes? Yeah, some nods here and there. Cool. All right. So Istio is a technology that was mainly conceived to be a service mesh, right? So it's an interesting concept, super complex as well, but it's totally worth it to learn. Because Istio is not only a service mesh, it also injects failure into your system so you can actually see how it behaves. So that's what I like a lot. So I'm just going to show some real configuration in Istio, basically. So hopefully this is going to work. Hold on. Yeah, okay, so here we have a dashboard that basically shows how the system is behaving. and it shows the request per second. And somewhere here that I forgot, oh, here it is. So I have some animation as well showing the traffic. This is real traffic from a staging environment that I have somewhere. And services are running here and requests are running here. And let's say that one of these services actually starts failing. So this is going to become red at some point. And it's going to say why it's failing. So all of those things that I shown before basically are implemented by Istio. So normally you have circuit breakers out of the box. You don't have to implement it on your service. Someone else is doing that for you. You just have to configure it. It will implement the load balancing algorithm that I mentioned as well. It will make sure you have essentially like the outlier service hold detection. If something goes off, it replaces, and Kubernetes kind of brings up to you a new instance of that service. And what I like a lot is the fault injection part. So here's an example of configuration in a very, very simple configuration for a virtual service inside Istio. So forget about the virtual service part because that's Istio, but look at this part right here. It's probably too small for people in the back. Hold on. Hopefully this will go up or not. Yeah, forget about it. So here what we have is basically a fault injection, right? So Istio allows you to inject failure into your system and then you can see how it behaves. So here we're saying, okay, we're gonna do for every request that has this exact header called JSON with A, we're gonna actually do a delay of 7 seconds for every request, and the percentage value here is 100. So if you want only 50% of the request to fail or to delay, you put 50% there, and you put the fixed delay time, and then it will basically see how your system behaves. Of course, you can do delay, you can do really the other part here, like HTTP status, like 500s, random 500s, random 401s, 403s, just to see how your system behaves overall. This is normally for HTTP, but you can also do that in gRPC connections, TCP connection level. You can fake your database, for instance, say, well, if your database is not there, how your app behaves, how your whole system behaves. It's not exactly chaos monkey style, but it's definitely fault injection, which is super cool. With Istio, though, and Kube and Kubernetes, you can basically do a chaos mesh, which is super cool as well, where you can really have the test scenarios and you can have the failure scenarios and then inject that in a point in time across your cluster. And then you can monitor it, how they respond, how the traffic level responds, how the load system responds, and then Kubernetes kind of will put that in Grafana for you so you can see the metrics. You can see how your service is basically working. So this is very Kubernetes specific, but if you use it, maybe you want to explore it because it's super useful and super interesting as well. So yeah, back here. None of this is useful if you don't know what's going on, right? So let's say that you implement all of these interesting patterns, but you don't really measure it. You probably know, because a lot of people say you should measure everything you do, even before you start doing it. If you go to a new system, you probably want to see some metrics of that system that already exists before even touching it. So for metrics, normally in Go, or in Java, actually, we use something called OpenCensus, which is it's a platform that it's a standard that actually implements many different libraries on how to measure metrics, how to have metrics in your systems that are standardized across all languages, which is a trouble when you have a big company with different languages and you know this different ecosystem, and trying to standardize metrics is just a nightmare. So this will actually make sure you have a standard metric system across any language. And then you can have dashboards and things like that. So normally you have metrics, you have a distributed tracing as well, which is super useful for debugging. So if you have problems in your system, distributed tracing is normally what you look at. Jaeger is our choice normally these days. But there are many others like Zipkin or other tools. So OpenCensus is the tool that I mentioned before. OpenTracing is the standard for distributed tracing that it's used most these days. And OpenTelemetry is going to be the one that will converge those two, which is coming out this year, I think, hopefully, for all languages as well, all major languages. which is super, super cool. So yeah, this is me, not this. This is me. And yeah, if you want to see the design for failure, here I have an example running in Kubernetes with all those examples that I mentioned that you can run by yourself. And here, because I like coffee quite a lot, there's an example of a coffee shop, really like a barista service, and then I have the order service and a bunch of other small services that play along together. And sometimes the order fails and the barista cannot actually do something. And then you see the system actually failing by itself. Also runs in Cube, and you can just run it. Thank you. And if you have questions, please do ask me. Yay. Is there any question? Any curiosity? Cool.
TLS is work only on Kubernetes environment or any other infrastructure also?
Sorry, the first part?
The service mesh you are
The service mesh.
yeah. Only for Kubernetes or any other?
Not quite. Like Istio was developed to work in any environment, even on premise. It's a C++ installation basically. It's just a binary in the end. So it runs by itself. As long as you have Docker, it will be fine.
Okay.
So you can run it even in the one from Nomad. There we go. Even on Nomad, you can still run it. Yeah. We were trying to use this at N26 because we used Nomad there for a while. It works well. Cool. Any other question? Cool. Think we're good? Well, you can reach me out. I'm going to be here for some drinks. Cool. Thank you very much. Appreciate it.